Okay, welcome to Unit 3.3, Thermodynamics, Part 1.2. So the last one in 1.1, we just did a recap. And what we're going to do here is we are going to start looking at what's known as Hess's Law, which is another way that we can calculate delta G and also other thermodynamic terms such as delta H, delta S, etc. So in addition to having the delta G equals delta H minus T delta S equation, we now have this Hess's law, which is using the standard change in Gibbs free energy or enthalpy or standard entropy of formation, and its products minus reactants. So the sum of products minus the sum of reactants in all three cases. So as you can see, all the equations pretty much look alike. Except for the terms that we're using, whether delta G, delta H, delta S. And although we're not going to calculate that until part 2 of this video, we are going to talk about what it's meant by free energy of formation, because this is a very common question. It comes up a lot. So you really need to know what free energy of formation is. So here's the definition. In terms of changing Gibbs free energy, delta G F naught, or this F here standing for formation. So the standard in Gibbs free energy of formation is a change in Gibbs free energy for the synthesis, so making of 1 mole of a substance from its elements in the standard state. So you are making 1 mole of that substance from its elements in the standard state. So let's break that down by looking at an example. There's a table, it's called Appendix C, that you'll have that's linked to this assignment, and I'll give you a hard copy next week. So the delta G standard of formation of H2O is this value here. There is a chemical reaction equation that's associated with this delta G. So basically the delta G standard formation for H2O is measuring the change in Gibbs free energy for the formation of H2O from elements in the standard state. How do we figure that out? Well, let's first of all look at what H2O is made of. It's made up of 2 types of elements, hydrogen, and hydrogen in its standard state is H2 gas. So that's something that you'll have to start to know, is that the way that we experience hydrogen on Earth, typically we experience it as H2 gas. That's what it means, like the standard form of H2, of hydrogen on Earth. For oxygen, which is the other element it's made of, the standard way that we experience oxygen on Earth is as O2 gas, not as a liquid, not as a solid, not as O3, but on Earth it's typically, when we experience oxygen in its element form, it's O2, and it's a gas. So these two are going to be the reactants that are used to make H2O. And so we write them out here. H2 plus O2 goes to form H2O. So we're almost done. The last thing that we need to consider is, in addition to forming H2O from its elements in standard state, we also need to know that we're only going to form 1 mole of it. So the coefficient in front of H2O must remain 1. And then we're going to use that to sort of balance the rest of the equation. So keep that 1 as 1 and then then put the correct coefficients in front of your reactants. Now, in order for that to happen, there are going to be times when we have fractions or decimals. So in this case, in order for this to balance out, we would need 1 H2 gas and then a half mole of O2 gas. And so this reaction here, as written, the delta G of this reaction is negative 237.13 kilojoules per mole, and that's how we got the delta G standard formation. All right, we can do the same thing. Let's quickly look at this example with sodium nitrate. So you can do the same thing for anything else. This is the delta G standard of formation right here. How do we get that? Sodium nitrate is made up of sodium. The standard state of sodium, it's a metal, so it's going to be solid. The standard state of nitrogen is N2 gas. The standard state of oxygen is O2 gas. And so all these 3 things are going to become the reactants. Our product is NaNO3 solid. Well, then we know we want 1 mole of our product, and then we change the coefficients accordingly. Let's see if you can do it. So I would pause the video now and see if you can figure out what the coefficients are going to be. All right, so what you may know is that sodium would be 1. the coefficient in front of N2 will be 1/2 because 1/2 times 2 will give us 1, which we have only 1 nitrogen on that side. And then for oxygen, it's going to be 3/2 because 3/2 times the 2 here will give us 3, and we have 3 oxygens on the product side. All right, so that's the way we write the entropy of formation reactions. But it's not as important to write them as it is to recognize them. So let's see what we mean by that. Which of the following is a standard formation reaction for CH3OH, which is methanol? So take a moment, see if you can figure it out. Pause the video now, and then when you press play again, the answer will be revealed. All right, so the answer is D. So let's just take a quick look. CH3 is made up of carbon, and the standard state of carbon is graphite, solid graphite. It also has hydrogens, and the standard state of hydrogen is hydrogen gas. And it also has oxygen, the standard state of oxygen is O2 gas. All right, so why is the answer D and not some other answer? If you look at choice A and B, those are wrong. One of the reasons why they're wrong is because CH3OH should be on the product side since you're forming it. And it's on the reactant side, so we can kind of automatically cross those out. You can also cross out A because it doesn't have elements in the standard state, H2O and CO2. The C is almost correct. However, we need to form 1 mole of CH3OH. Remember, for standard formation, it's always going to be, the product should have have a coefficient of 1 because you're only forming 1 mole of it. So that's why C is incorrect. And the answer is D. All right, you're going to try it now for iron 3 oxide. So what's the standard formation reaction for iron 3 oxide? Pause the video now. When you press play again, the answer will be revealed. Great. The answer again is choice D. So you're forming 1 mole of this product here from the elements in the standard state. The reason why C doesn't work, if you look at C, O3 is not oxygen in standard state, so you got to be careful about that. It has to be elements in the standard state. Okay, so in addition to being able to recognize the formation reactions, you also need to be able to calculate, to use the delta G of formation to calculate delta G of a related reaction. So let's take an example, look at an example problem. Let's say we were asked for, what is the delta G for the combustion of iron? So here's the reaction. And right now we have no information to go by. We don't have delta H, we don't have delta S, we don't have the temperature. So how can you sort of figure this out? Well, if you take a closer look, you'll see that the reaction is actually the delta G formation reaction just doubled. What do I mean by that? The delta G formation reaction of iron oxide is this. We're producing 1 mole of iron oxide from iron solid and O2 gas. And that sort of like matches up. What's the main difference between them is that the coefficients in the reaction in pink are doubled. So that means that all we did was just double this reaction here, the formation reaction. And since we doubled the formation reaction, all we need to do is double the delta G of formation in order to get to the delta G of the reaction at the top. So delta G in pink is going to equal to 2 times the delta G of formation. And that's how we get this value. So if you take a look at the process that we did here, we first had to recognize that this reaction is related to a formation reaction. And so once we had that, then we had to figure out what we did to go from the formation reaction to this reaction. In this case, we had to double it. So that means, and we do the same thing to our delta G of formation, we just double that value. And by the way, these values, again, are listed in that table here, the appendix, so you can always figure that out. Okay, if you're asked for what's the delta G for the decomposition of water by electrolysis, so here is the reaction, and you're taking a look at that. Why don't you pause the video now, see if you can figure out what you would do, similar to example 1, to figure out the delta G of this reaction. Okay, so first thing is you got to recognize what the delta G of formation reaction is. You have water and you have elements in their standard state. So the only thing is that water is on the reactant side, and if it's delta G of formation, it would be on the product side. So that means that one thing that we did in going from the formation reaction to the reaction in pink is that we flipped the reaction. The other thing that we'll notice is that we have 2 moles of water instead of 1, and for the formation reactions, we would only just have 1 of the mole of the compound. So therefore, we did 2 things here. We flipped the the reaction and we doubled it. And so that means we have to do the same thing to delta G formation, which is this value here. And when we say flipped, in terms of mathematically speaking, what we mean is we're flipping the sign. So what we're going to do is we're going to take this reaction, the delta G of formation, standard delta G of formation, and multiply it by -2. 2 for doubling and negative because we flipped it. And when we do that, we get this value. Okay, so in summary, if you have to flip the standard formation reaction, then you flip the sign of delta G. And if you have to multiply the coefficient of the standard formation reaction, multiply the coefficients as well. And when I say multiply, that can also mean divide. Maybe you're dividing by 2 instead of multiplying by 2. That's fine. All right, you're going to try it with these CFUs. So take a moment, read the CFU, and pause the video now. When you press play again, the answer will be revealed. Okay, so here is the answer. This is a standard formation reaction for NH3. We had to flip it and multiply it by 2. So we had to flip this and multiply it by 2 to get to here. And then that gave us our delta G value. Notice that our units are in kilojoules, not kilojoules per mole anymore, because this 2 is technically multiplying by 2 moles. All right, try it again for CFU 4. Pause the video now, read it, and then when you press play again, the answer will be revealed. Okay, great. So the reaction here, again, the standard formation reaction, you're going to flip it. Actually, you don't have to flip it, but you do need to, because the O2 and the O3s are on the same side. But the one thing you do need to do is you need to divide this reaction by 2 or multiply it. Multiply the standard formation reaction by 3. And so to get to this reaction. So we're going to multiply our delta G standard formation by 3 as well. And then we get this value. Okay, finally, we're going to take some notes on elements in their standard state. So Appendix C, which is linked, and you'll get a hard copy next week, has the value delta H, delta G formation, delta H formation, and then S formation. Notice that for the entropies, there's no delta. It's actually measuring the amount contained, not related to a change. And the delta H of formation, delta G of formation for elements in their standard state are going to equal, and this is super important, 0. Oops, the line got switched. But anyway, it's going to equal 0. So that's what you're going to fill in this blank here. And that's because you would be forming those elements from themselves, so there is no change. Now, on the other hand, delta S of formation, this actually is supposed to go in this line below, does not equal 0. So that part does not equal 0. So, and it's not delta S, but S of formation does not equal 0. And so an example of that is P for S white here. You can see the delta H for formation, delta G of formation are both zeros, but for delta S, it's not. So this is the phosphorus in the standard state. Okay, final note is that not all elements, and you should be able to see this on your handout, I hope it's getting messed up here a little bit, not all elements are in their standard state. So for example, phosphorus, you see all these different elements of phosphorus that are listed here. Only one of them is in the standard state, and that is the P4 S white. So that's the one that's in the standard state. And you know this because delta H is 0 and delta G is 0. So that's how you would be able to tell from the table if an element's in their standard state. All right, you're going to try this with CFU 5 using the appendix. You're going to look for carbon, hydrogen, oxygen, fluorine, chlorine, and sodium. Identify the values in their standard state, or these elements in their standard state. And you're going to use the thermodynamic quantities to help you do that. So you should be looking for delta G and delta H of formation equal to 0. Okay, so here is the answer. Again, the way that you would find that is if you look in the table, if the delta G's and delta H of formations are equal to 0, then those are elements in the standard state. Okay, and final note here is that there are some very common diatomics, meaning things that have this formula like X2, which means they're di, meaning two atoms together. So H2, N2, O2, F2, Cl2, Br2, I2. These are very common, so you ought to know these. Just sort of memorize that these are the ones that they're going to be gases, and they're going to have a subscript of 2 in their standard state because they're like 2 atoms that are together. All right, that's it for part 1.2. The next video is part 2.